Today on the Perception and Action podcast, what is Biotensegrity? How can it be used to understand movement coordination and movement preparation on an individual level, and also be used as a model for team coordination? How does it relate to Bernstein's concepts of motor synergy and muscle tone? So it's time for a call to action. Hello, and thanks for joining me. This is Rob Gray from Arizona State University. I've been on a now over 25-year journey as a researcher, professor, and high-performance consultant to understand how we acquire and adapt our perceptual motor skills. Welcome to the Perception and Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. If you're a coach or an instructor, my goal is to help you bridge the gap between research and application, and to connect your experiential knowledge with skill acquisition and motor learning theory. I want to help take you from using practice design recipes to becoming a master chef who can manipulate the key ingredients to come up with your own innovative training methods. If you're a student or fellow academic working in the skill acquisition field, I hope to keep you up to date on the latest studies and help you get to know the people working in this area. Finally, if you're developing training technologies, I hope to help you incorporate good motor learning principles in your design, pull out key performance metrics from the data, and design effective studies to evaluate your product. To learn more, help support the podcast, and or work directly with me, please check out perceptionaction.com. Now on to the show. In today's episode, I want to look at the very interesting and fairly complex topic of biotensegrity, focusing on why we should care about it when trying to understand skill acquisition and movement coordination. For me personally, this is really my first deep dive into the topic, so I'm only going to try and cover the basics here. If you're interested in more specifics, please check out the links to the articles in the show notes for this episode. So here we go. To illustrate the concept of tensegrity, I want to start talking about architecture and structures. Think about Stonehenge for a second. How is its structure and shape maintained? It is through an external force consistently acting on its components, gravity. What would happen if we took a very large backhoe, scooped Stonehenge out of the ground, and launched it into space? Its structure would be lost as all the components, the large rocks, would move in different directions because there's no longer gravity present. Most human-made structures are like this. They are stabilized through the external force or compression of gravity. Next, I want to think about tents. Think about the modern one that most people use when camping now, the pop-up tent. You know, the ones that immediately pop into shape as soon as you take them out of the bag? What we have here is an example of tensegrity. The structure is created by a balance of internal forces, the tension created by the internal tent poles sewn into the material, not some external force. Once we pull the tent out of the bag, we can pick it up and move it around to another location, or we could launch it into space and it wouldn't lose its shape. As the name implies, tensegrity means integrity through tension. The structure of the tent is maintained by the internal balance of tension between the poles, not external compression from some outside force. In fact, external forces, applied when you shove it back into the bag, are needed to prevent it from keeping its shape. Tensegrity is an architectural principle first put forth by Fuller in the 1960s. Its technical definition is: a tensegrity state is a stable, self-equilibrated state of a system containing a discontinuous set of compressed components inside a continuum of a tension component. There are many examples of it that can be now found in buildings. For example, the Needle Tower in Washington, D.C., the Munich Olympic Stadium, and Montreal's Biosphere. Why would we want this? Because it has some important properties. First, because a tensegrity system is pre-stressed, that is, it starts in a state of intrinsic tension, it allows for fast responses to stresses applied anywhere in the system. If you push on the side of a tent, such that one of the poles move, the tension between them will cause the others to move in kind, leading to the structure being maintained. The system does not need to establish its structure first, then respond to perturbation. It only needs to maintain its structure. As we will see, this idea of pre-stressing or pre-tension is very important for the control of movement. Second, tensegrity systems have energetic efficiency. Such systems maintain their structure in a highly efficient manner because the components work together and the system is essentially storing energy itself. Third, tensegrity systems become stronger when subjected to higher forces. I will get to that more in a moment. Finally, as we've discussed, tensegrity systems can maintain their structure and functional properties independent of gravity. This gives them what is called omnidirectional stability. Stability in all directions, not just when the system is oriented in the direction of gravity. Why are we talking about architecture and tense on a podcast focused on skill acquisition? Because it's been proposed that the human body is a tensegrity system, thus the name Biotensegrity. The basic idea is that the bones, muscles, tendons, etc. in the human body work like the poles and ropes of a tent to maintain the structure and posture through internal tension without the need for external forces. Rather than maintaining stability due to compressional forces from gravity, we achieve stability through internal tension. Each body posture we put ourselves in corresponds to a different state of pre-stress or intrinsic tension across the parts of our body. This gives us all the advantages of architectural tensegrity systems we just discussed. For specifics on the exact anatomical structures that might be involved, I would recommend checking out the 2014 article by Turvey and Fonseca. The concept of biotensegrity connects really nicely with some of the core concepts in the ecological approach to skill acquisition. As first noted by Turvey and Fonseca, tensegrity is a good biological model for Bernstein's level of synergies. As I've discussed many times on the podcast before, at the highest level of skill, Bernstein proposed that the degrees of freedom problem is solved through the development of motor synergies. That is, instead of freezing joints or having them work independently, they work together in synergy to compensate for each other. A shoulder rotation that is too slow to get the hand to the ball is compensated for by speeding up the extension of the elbow a little. Well, if you think about it, this is exactly what occurs in a biotensegrity system. Once my tent is set up, pushing on one of the poles will lead to compensatory bending of the others. Contrast that again with what would happen with Stonehenge. If we pushed one of the stones with a really large external force, the other stones would not move at all. The idea of pre-stress or intrinsic tension in a tensegrity system also nicely connects with Bernstein's ideas related to muscle tone or tonus. To quote an article by Calderia and colleagues that I will discuss in detail in a little bit, Bernstein's work was fundamental to understand motor control, coordination, and the mechanisms whereby functional units combine to reduce the number of degrees of freedom for meeting task demands. To organize complex global movements, the muscular skeletal system is supported by the basement level of tone, which corresponds to the pre-stress property of tensegrity structures. The architecture at the level of tonus is a multifractal biotensegrity system exhibiting pre-stress at all levels, which allows system stability and fast adaptation to mechanical perturbations by redistribution of tension." End quote. Stated another way, the pre-stress or tonus sets a biotensegrity system up nicely for implementing motor synergies. When tension is established, the system is highly sensitive to any external perturbation and can adjust globally, with the components working together in response to it. These ideas also have important practical implications for sport, as can be understood when looking at the concept of muscle slack that Franz Bosch talks about in his books. Imagine you're going to try to walk across a length of loose rope. Before we can attempt the crossing, we're going to need to wait for the rope to be tensed and pulled taut. This situation is equivalent to having slack in the muscles when performing an action in sports. When there is muscle slack, the system will be less responsive to external forces and will take longer to generate any forces that the athlete is trying to generate. Essentially, they have to wait until the system reaches pre-tension first. This has led Franz to make the strong conclusion that, quote, "the speed at which muscles can build up their tension and overcome muscle slack is usually more important to performance than the amount of force they can eventually produce. Counter movements and co-contraction prior to executing a movement create a biotensegrity system that has all the advantages we've been discussing. For specific exercises an athlete can do to remove muscle slack, check out Franz's book. A final critical aspect of a biotensegrity system is that it works through a process of self-organization, and is consistent with concepts of coordinative structures I discussed back in episode 157. To finish off the quote I used from Caldeira and colleagues a few moments ago, the architecture at the level of tonus is a multifractal biotensegrity system exhibiting pre-stress at all levels, which allows system stability and fast adaptation to mechanical perturbations by redistribution of tension. This pre-stress characteristic conveys the necessary support for self-organizing processes that enables synergies. From an ecological dynamics perspective, synergies express relationships between their components, namely cooperation among components' contextual roles to achieve a task goal." End quote. Again, think about our tent. When we push on it, there's no executive command or motor plan about how to react. The poles organize themselves to maintain the structure. Like other self-organizing systems, this leads to complex, often unpredictable outcomes. For example, tensegrity systems often exhibit what is called nonlinear stiffening, in which the application of higher forces actually leads to the system being stronger and more stable than with lower forces. The link between these different concepts is discussed nicely in a commentary on a Latache article published by Paula Silva and colleagues in 2010. In the main article, Latache is proposing that coordination is achieved through a combination of an equilibrium point and motor synergies. The equilibrium point hypothesis is a topic I discussed back in episode 151. The basic idea is conceptually similar to that of a coordinative structure. The system sets itself with an overall goal to be achieved, the equation of constraint in a coordinative structure or an equilibrium point, but then allows the components to self-organize and work together to achieve it. Critically, to achieve motor synergies in this type of system, one cannot just use the positions of the body, but rather needs information about how they relate to each other, which Latache proposes involves a network of soft connected tissue. And here is where our topic du jour comes in. To quote the Silva et al. Article, in several respects, the foregoing characterization of the connective tissue network suggests that the musculoskeletal system is organized as a tensegrity structure. Tensegrity structures are unique mechanical systems that derive their support function and mechanical stability from continuous tension and local intermittent compression. At the level of the body, the bones can be thought of as compression members which are embedded in and balanced by the tight interconnected soft tissue network, muscles, ligaments, and fascia, that constitutes the tension-bearing structures. As a result of pre-stress, activities occurring locally in multiple parts and at multiple levels of the system coordinate naturally to re-establish a force balance should it be disturbed by mechanical forces within and adjacent to the system. Thanks to this force balance constraint, the global deformations of a tensegrity structure are lawfully related to such mechanical forces, and hence informative about them. Although multiple mechanoreceptors are active at the multiple locations during such interactions, rapid integration to a few degrees of freedom would be possible in principle with the force balance property allowed by a biotensegrity architectural organization. As a result, tension distributions and their changes, due to internal or external forces, may be registered at the level of the body as a unit, with the former related to the postural states and the latter related to their transitions." End quote. So in sum, a tensegrity structure seems to be a perfect fit for using a control structure like a coordinative structure or an equilibrium point. This is nicely described in a quote by Skelton and Oliveira. Quote, "The main motivation for the use of tensegrity structures is the advantages of integrating control functions within the design of the structure itself. The idea of controlled tensegrity systems is to allow the dynamics of the controller and the dynamics of the structure to cooperate more fully. This is accomplished by using control to change the equilibrium of the structure rather than pressing against a relaxed equilibrium of the structure." End quote. The final idea I want to consider in today's episode is that tensegrity might not only apply to an individual body, but could also be used to understand the coordination between multiple bodies, that is, team coordination in sports. This interesting idea was discussed in the aforementioned 2020 article by Caldeira and colleagues. Of course, one of the main differences between a team-level tensegrity system and the ones that we've been discussing so far is that there are no physical connections between the players on a team. There is no connective tissue that can be used to create pretension and allow for synergies to occur. As an alternative, the authors propose that the components of the system are linked on an informational level rather than a physical one. In particular, the shared affordances picked up from the environment. As I discussed back in episode 117, this information can constrain the team behavior in a similar manner to the way mechanical forces constrain movement within our body. The authors then attempt to relate team coordination to the key properties of tensegrity. First, what constitutes pre-stress or intrinsic tension in team sports? For this, the authors propose, quote, "Intrinsic tension is created by past experience, the team sport skill learning, the common path that characterizes a given team when they arrive at the performance context, and the learn and practice processes, including acting and perceiving affordances of others and for others. Also, more permanent environmental constraints such as rules or court dimensions influence intrinsic tension. All of these constraints confer information omnipresent within the system formed by a sports team." They further propose that if a team has this intrinsic informational pre-tension, they will be quicker and more flexible in responding to changing environmental constraints. For example, a situation that affords attacking or defending. Quote, the players adjust their actions to the information available in every moment, which means that they change over time the structure they form, and thus they change the team's informational tension. The challenge is to keep the informational tension in a dynamic state that provides structure and team stability and ensures responsiveness. End quote. By maintaining a structure that's held together internally by information, rather than externally by a coach's explicit instructions about where to be and where to go on the field, the team can have the fast, adaptive flexibility I discussed in my last episode. A loss of a tensegrity system leads to, quote, a loss of efficiency in the structure that can be linked to more uncoordinated actions such as unnecessary redundancies, for example, players invading each other's areas of responsibility, or detrimental delays. For example, players not positioning favorably to perform his or her share of or to compensate for teammates' less successful actions. End quote. Like a physical tensegrity system, a team-level system maintains stability through self-organization. Considering a team as a group-tensegrity structure, the players' perception and action processes allow the tensegrity structure to emerge. While team actions can be highly plastic and dependent on immediate constraints, they may also benefit from and usually rely on strategy or design based on players' spatial distribution. For example, it's common for players to have so-called areas of responsibility in defending or attacking. Finally, the authors sum up their view. From the group-tensegrity hypothesis we are presenting, external constraints acting on the structure are mainly informational and omnipresent over time. Therefore, stability must be dynamic. In a weak team's organization, its geometrical configuration stable at one point in time might lose stability as the context unfolds. Only geometrical team configurations capable of sustaining tensegrity-like properties will ensure adaptive dynamic stability. End quote. So to sum up today's episode, I think the concept of biotensegrity is highly relevant to understanding sports performance on both an individual and team level. It connects nicely with existing ideas like coordinative structures and motor synergies, and it also has important practical implications for coaching. On an individual level, it's critical that an athlete learn to be able to remove muscle slack, to be able to take full advantage of a tensegrity system when executing a skillful movement. While on a team level, the tension created by shared affordances and informational constraints can make a team more adaptive and flexible. The key in both cases is understanding how we can develop this pretension and links between the components of the system. Okay, that's it for today's episode. Remember, you can contact me at robgray@asu.edu or follow me on Twitter at ShakyWeights. To find out more about the podcast, please check out perceptionaction.com. Finally, to support the podcast and receive bonus materials, including written transcripts, please head over to patreon.com/perceptionaction. This is Rob Gray from ASU. Cheers for now, and keep them coupled.